Hello, welcome to a series of videos I'm going to be doing on solving ordinary and partial differential equations computationally. I'll show you some of the mathematics behind these ideas, in particular the mathematics behind the numerical algorithms. So we'll start with ordinary differential equations, or ODEs, and we'll progress through a series of videos up to solving some partial differential equations, including nonlinear partial differential equations. To get started, the first thing you can really look at is Euler's method. Some of you might have seen this in an ordinary differential equations class, but if not, all you need is a bit of a background in differential calculus. First, let's take a look at a standard differential equation. So we might have something like this. dy dt is equal to some function of t and y, where here f is given, y is a function of t, and it's unknown. With differential equations, your unknown is an entire function. On top of this, we usually have some kind of data, such as initial data, to solve this equation. So we might have something like y at some initial time is equal to y0. So here, t0 is a given initial time, y0 is a given initial data. Now, these subscripts don't necessarily mean that we're starting at 0. They just mean sort of the starting place, the 0th place where we start. Let's look at an example. We might have something like dy dt equals 6 minus t times y, and some initial data like y of 3, it's equal to 2. Now it turns out that because this equation is linear, it can be solved, for example, by the method of integrating factors that you might see in a differential equations course. However, the result has a kind of non-standard or non-trivial integral in it that can't be expressed in terms of simpler functions. So we'll try to solve this with a numerical method. In particular, let's try to approximate the value of this at one value in time. So our goal will be to approximate y at time 4. In order to do this, let's use Euler's method. So Euler was really the first person to write down a numerical method for systematically solving differential equations of this type. Here's some motivation for Euler's method. First, we remember that the derivative is defined by a limit as delta t goes to 0 of y at t plus delta t minus y of t divided by delta t. So this means that this is approximately equal to y at t plus delta t minus y at t divided by delta t for small t, right? Because t is going to 0, so this approximation will get better and better for small delta t. So what does this mean? This means that we can use this approximation in our differential equation. Let's write down our differential equation, dy dt equals f at t comma y, and let's make the dependence on t explicit there. This can be approximated by y at t plus delta t minus y at t all divided by delta t. This gives us an update formula for our solution. So let's see how this works. So that is, and here we're solving for y at t plus delta t. We'll get y at t plus delta t. We can multiply by this delta t to the right-hand side and then add y of t to the right-hand side to get y at t plus delta t is approximately equal to y of t plus delta t times f of t comma y of t. And this is almost Euler's method. Euler's method just takes this one more step to say that we are actually going to use this approximation as an equality, which will not give us the correct solution necessarily, but will approximate the solution hopefully well. So Euler's method is the following. Given yn, which we could think about as some kind of approximation of y, the exact solution at time tn, determine yn plus 1, which we're thinking about as an approximation of y at the next time step, and we just mirror what is happening above. So we have this y at t plus delta t, that's like the next y at the next time step, and we'll set this equal to y at the current time step plus delta t f t comma y n. And technically this might not actually be y at the current step, this might just be our best approximation to y at the current time step, but this is Euler's method. Now you might say, well, okay, if this is great, if I knew what yn was, then I could get the next one, but how do I know what yn is, right? We do know one value, so we know also that y at t0 is equal to this, is equal to some initial value, which we've called y0 here. So in some sense, since we know the initial value, we can march forward with Euler's method. So that's the idea. Let's see how this works in an example. So if we consider, again, this differential equation dy dt equals 6 minus ty, and then make it an initial value problem by saying y at time 3 it's equal to 2, then for our Euler's method, we're thinking about this right-hand side. This is our f of t comma y, right? It's equal to 6 minus ty. So Euler's method becomes, for this problem, yn plus 1 is equal to yn plus delta t times f at tn yn. Actually, this is for any right-hand side. For our problem, this would be yn plus delta t. And now we'll just fill in these values for f. So f looks like 6 minus t, but we're plugging in tn. So that's a tn there. And then we're plugging in yn, so we get a yn there. So this is Euler's method for this problem. Now, one of the things we have to decide on is what is our time step going to be. And this is a user input choice. The smaller the time step, the smaller the delta t, the more accurate answer we expect to get. But for ease of calculation, I'll just choose for now delta t equals 0.5. So choose delta t is 0.5, which would be pretty big for most real-world applications, maybe too big. But for this application, we're just trying to get our hands dirty with some calculations and see how it works. So we'll choose delta t to be this, and again, we're going to approximate y at time 4, right, with our initial time is 3, and y of 0 was 2. Okay, so let's see how that works. So for Euler's method, we'll set n equal to 0 to get started with, right? That means here, n plus 1 will just be 1 because n is 0. And here we'll get a y of 0, or y sub 0, I should say. So this would be y1 equals y0 plus delta t times 6 minus tn. So n is 0, so this will be t0, y0. So this is the n equals 0 case. If we now fill in our values, we have 2 plus 0.5, right? That's our delta t. And then 6 minus t0 is 3, y0 is 2. And so we get 6 minus 3 times 2 is 0. So this just becomes 2 plus 0, or 2. Okay, so not very exciting. We started with 2 and we ended with 2, but that's just because this thing became 0. Now you might think that it just continues to be 0 each time, but don't forget our time will be updated. So let's keep track of our time as well. So and t1, time is easy to update. You just add on your time step delta t. So this is just 3 plus 0.5, or 3.5. To go a little bit further, remember, because y1 is an approximation of y at t0 plus delta t, which is y at 3.5. So y1, we've taken a step of 1/2 in time. We need to take another half step to get all the way up to t equals 4. So that means we should stop at the n equals 1 case, right? So when n is equal to 1, we have y at 1 plus 1 down here, right? Because it's n plus 1. n is 1, so 1 plus 1 will be 2. And then on the right-hand side, we just follow Euler's method again. It's y1, this is yn, plus delta t times f at t1, comma y1. Just repeating Euler's method. But again, this is y1 plus delta t. Now filling in our specific value for f, we get here 6 minus t1 y1. And using our values that we calculated above, we had y1 is 2. Delta t is 0.5 all the time. It's just a uniform time step, the same time step size every single time. And then plus 6 minus, well, t1 is 3.5 now. And y1 we found to be 2. So here we get 2 plus 0.5. 3.5 times 2, that's 7. 6 minus 7 is negative 1. So we have 2 minus a half, so we get 1.5. Now it turns out that the exact value of y of 4 is approximately 1.612. So we're pretty close with just a time step of 0.5. If we wanted to get a better approximation, then we could use a smaller time step. So for instance, we could use delta t equals, before we chose it to be a half, now we could choose it to be a quarter, 0.25. Then, right, we would still have y0 is equal to our initial condition. y1, though, would not be an approximation to y at time 3.5, but this would be an approximation to the exact solution at time 3.25. And y2 would be an approximation to y at 3.5. y3 would be at another delta t, so we get 3.75. And finally, y4 would be an approximation of y at 4. And it's just a coincidence that there's a 4 here and a 4 here. This just means we had to take 4 steps of size a quarter to march from all the way from time 0, right? Because this is equal to y at 3. To march all the way from 3 down to 4 with step sizes of a quarter, we had to take 4 steps. Okay, so I'll leave it as an exercise for you guys to work that out in the comments. But this is how you would use Euler's method by hand. Now, doing these computations by hand can be very laborious. So in the next video, we'll see how to speed these computations up quite a bit using a computer. So we'll see this in the next video. And until then, have fun.